Hello, this is Team 49, made up of Blake Beard, Phil Fedor, and Cameron Haynes, presenting the Safe, Weightless Gym. The agenda of this PowerPoint will proceed as follows. Starting with the problem statement, then we will go into our vision, describe our objectives and constraints. We'll talk about the research that we did and the numbers that we calculated. We will follow up with our planning, the functional design, and finish with the concerns and conclusions we'll proceed with for next semester.
The problem statement begins with a quote from Science Daily. Between 1990 and 2007, about 1 million people were injured in weightlifting-related activities, with over 65% of them being from dropping a free weight on themselves. So in order to attempt to combat these injuries, our goal is to create a weightless gym system with safety features in place that will prevent any injuries in the future in case of dropping or mishandling the equipment, while also keeping the wide range of exercises available.
So as Cameron described, there are issues with free weights. This is just an example of the problems that can occur in a gym with lifting free weights. As you can tell, this person does not have a spotter while he's about to attempt this large amount of weight over his suspended body. As you can see, there are more than just problems with not having a spotter. He did try to realize this and put these bars here that would help, except for the fact that he clearly missed them, and so these in themselves have their own flaws. There are much worse videos on YouTube that I could have showed you where people actually end up dying, unfortunately, but I felt that would be too graphic for this presentation.
So this was our original vision for the Safe Weightless Gym. We wanted to be able to eliminate the risk of injury by not using weights, and also have safety features in place that will allow, just in case the bar itself gets dropped on you, that it won't hurt you. We wanted it to be simple and easy to use. We wanted it to be user controlled through the app, where they could select the amount of weight, a variable weight that they would like to lift. We wanted many different types of weightlifting activities to be available. And then we wanted it to also to be able to generate electricity. Some of our objectives, one is the ASTM F2276 standards, which is just the standards that we would have to meet to allow our system to be used in gyms today. We also want it to be safe and easy to use, as mentioned before. And then the natural feel, like I said, we don't want people to not want to use our weightlifting gym because it doesn't feel like a normal weightlifting system. So we wanted to have that natural feel, as well as a variable amount of weight, so that many different types of users can use it. We also want it to be compact and portable, but this only applies for full-scale implementation. We are currently pursuing a smaller scale implementation due to budget and power constraints. As you can see on the right, along with those standards, we are constrained by our budget. We just do not have enough money to build a full-scale design, as well as the amount of voltage and current required to supply a full-scale electric motor. So we are currently pursuing a smaller scale design.
So since we described the problems beforehand, our first idea of this weightless gym was that there was no motor or anything. It was just the entire gym itself was inside an electric field. So one problem you could probably think of is that maybe being inside an electric field with a lot of voltage could be some sort of hazardous. We weren't really sure about that. So we continued with the calculations And so the idea is that at the end of each bar has these point charges that can change in amount of charge, and then the electric field itself can also change. And so with these two changing resistances, it would allow the person to change that amount of resistance, and so that they can lift different weights and such. Except after doing some calculations, we realized that this would probably require something around 30,000 volts for only 200 pounds. And since we couldn't, like Cameron said, apply that amount of voltage with our constraints, we decided to move on to a different design. Our current design is based around this idea of a pulley machine. It can also be applied to the previous video that you saw. This is one of the great machines in the gym that can be used for multiple different exercises and such. So as you can see, there's a pin there, and the yellow pin that you would change the resistance. So our idea is to remove that and put a motor in place of it. This would be a programmable motor. And so with this programmable motor, the person would input how much weight they want to pull or do whatever exercise they want, and then it would act in the opposite direction to simulate the resistance needed for that amount of weight.
So here we have some background on how an electric motor works. In the middle, we have a magnetized core, and then current rotates through the wires on the outside, which pushes and pulls the motor from the electric field generated, causing rotation in the core. On the right, we have some of the basic equations we used to calculate our max force, torque, and input power and output power. So here we have some of the requirements for our full-scale implementation. We wanted our max force felt by the user to be around 200 pounds or 889 newtons to really allow a wide range of workouts. This means the max force output from the motor would have to be around 2 times more than that to make sure the motor doesn't burn out very quickly from always being near its max output. So that would require around 1,778 newtons. We estimated our radius to be around 0.02 meters. This would be the bar that rope would be wrapping around as the user lifts. And our theta would be 90 degrees because the rotation would be exactly 90 degrees from the upward pull from the user. And that gives us an estimated max torque of 35.56 Newton meters. We then estimated our angular velocity using a upward velocity from the user pulling of about 1 meter per second. And then using our 0.02 meter radius, we estimated around a 50 radian per second angular velocity. Using this and our torque, we think our power out would need to be at least 1,778 watts. And then using an 80% efficiency of the motor, which is about average for an electric motor, we think the power in would need to be around 2,222 watts. Because we can't currently meet this due to price constraints, we are settling with a smaller scale design. For this design, we have a power supply of 12 volts with a max current of 30 amps, which gives us a max power in of around 360 watts. Using the same efficiency as before, this means our max power out would be around 288 watts. Using the same angular velocity of 50 radians per second, our maximum torque would be around 5.76 Newton meters. And the maximum force felt by the user pulling would be around 288 newtons or 64 pounds. For our functional design of the end product, we would want the user to be able to use a smartphone to request a certain weight on the machine. The smartphone application would connect with a Wi-Fi direct network on a Raspberry Pi. The Raspberry Pi would continually loop through reading the current force from the user in the load cell, and then adjust the power to keep the force felt by the user to be around the desired weight. And the Raspberry Pi would also implement the safety for the user, where if the force is suddenly dropped very low, indicating that the user has dropped the weight, the motor can be shut off, and then the user will only have to worry about the weight of the bar, which will hopefully be very light, and can save the user from any injury.
So this is our Gantt chart for this first half of the year, up until Christmas break, where we currently are at. We did go through the selecting and buying of a motor phase. However, we bought a motor that was rated at about 1,000 watts. Is too much power than what these power supplies on campus can handle. So we sort of went through the using the motor to control speed phase. However, we're going to have to return that motor and buy a smaller motor, which works out. We learned a lot from this motor, and we believe that when we buy the 700 watt motor and then our power supply that we're going to use with it, that they will work well together. But doing this, we put ourselves a little bit behind schedule, but we plan to work a little bit over Christmas break so that we will have the motor in place by the beginning of the next semester. And then for the next semester, we plan to go straight into programming the UI as well as assembling the motor into a mechanical assembly that will be able to be a workout machine. We would like to have the weight of the assembly be controlled through the code, through the UI, and then we would like to program the safety sequences and start testing, preferably all before the beginning of March. The budget is centered around the motor. We need a pressure force load cell sensor, as well as the HX711 converter for that load cell sensor. The DC power supply that we are planning to buy is 12 volts, 30 amps. And then the 700 watt DC brush motor, it's 700 watt motor because of the 300 watts. We don't want to push it to its limits. We want it to operate about 50% of its capacity to increase the longevity, like Phil said before. And then the motor controller as well. We currently have a Raspberry Pi that we will also be using.
So going into next semester, we have a couple of concerns. Just the fact that we don't have the parts yet and having them all interact together might be an issue. We had that problem with the first parts that we bought. So naturally, it could just be a concern in the future. Also, building the mechanical portion could be a problem just because, like the pulley system, the user, we don't know if we don't have any mechanical background or we haven't designed this before. So that will probably be an issue, a learning experience, I should say. And then the pulley system with the feedback of the controller and the Raspberry Pi could be problematic depending on the rate at which the feedback occurs and how fast the motor can change its speed, just to make sure that the feel of the user lifting is natural and smooth. And then we also have one concern about the power source we're buying is that it doesn't plug directly into a wall, and so one end will be a three-prong input into the wall. The other end looks like we'll have to strip the wire and then connect it directly into the power source itself, which could provide a safety concern for the first time that we do that. But once it's all connected, it should be able to stay in place and not have a problem from there on. And so with these concerns and the planning that we have done so far, we believe that we can get back on track for next semester.
These are current references for the quotes, and thank you very much.